of materials. At the beginning of this chapter, we mentioned how the study of the mechanical properties of solids is extremely important for engineers designing heavy-duty, load-bearing structures. For example, when designing a building, it is extremely important for the engineer designing it to know the elastic properties of the materials that will be used to fabricate the columns, supports, and beams. Let us try to design a crane to carry a certain load for us. For a crane to lift an object, the object first has to be attached to a thick metal wire. This metal wire is then pulled up by means of pulleys and motors. Suppose we need to lift a 10 metric ton load. When lifting this load, it is important that the metal wire not deform or fracture. The stress on the wire thus must be in the elastic region, and the extension of the wire due to the load must not extend beyond the elastic limit. Let us use mild steel to design this wire. We know that mild steel has a yield strength psi of 300 × 106 Newton per square meter. The area of cross-section of the wire, therefore, must be at least A greater than or equal to W by psi, which is equal to mg by psi. This is further equal to 10 to the power 4 kilograms into 10 meter per second square, whole divided by 300 into 10 to the power 6 Newton per meter square. This is finally equal to 3.3 into 10 to the power minus 4 meter square. This is equivalent to a wire of circular cross-section with radius of 1 comfort. For the sake of safety, radius of the wire used is usually much larger than that obtained mathematically. Thus, we would probably use a wire with radius 3 centimeters instead of the 1 centimeter that we obtained. Since wire this thick would actually be a steel rod, we use wire made up of a large number of wires of smaller radii braided together. This eases manufacture of the wire while giving it greater strength and flexibility. Bridges and buildings involve structures which need to support extremely high loads. When designing such structures, it is important to ensure that application of a load does not lead to the bending of the support beams. Let us look at a beam loaded at the center and supported at the ends. A beam with length L, breadth B, and depth D, when loaded with a weight W at the center, sags by an amount delta equal to WL cube whole divided by 4BD cube Y. In order to reduce the bending of the beam, it is important that we use a material which has a large value of Young's modulus Y. Also, since the sag is inversely proportional to the cube of depth and the breadth of the beam, increasing the depth is more effective in reducing the sag of the material. The deep bar, however, may buckle if the load is not at the right place. This is difficult to achieve when we consider a bridge which has moving traffic on it. To prevent buckling, load-bearing beams are designed with an L-shaped cross-section. Pillars and columns in buildings and bridges are also built with distributed ends, so that they can support a greater load without compromising their structural integrity. The tallest mountain in the world, Mount Everest, has a height of 8.84 kilometers. But can there be a mountain taller than the Everest? And can mountains be infinitely tall? Let us find out. The base of a mountain is not under uniform compression. This provides some shearing stress to the rocks below, causing them to flow. For a mountain to exist in a stable fashion, the stress due to the combined weight of everything on top of the mountain should be less than the critical shearing stress of the rocks forming the base of the mountain. Let the height of the mountain be h.
The force per unit of the mountain is
h rho g.
Here,
Rho
is density of the material which makes up the mountain, and g is the acceleration due to gravity.
The shear force acting on the base of the mountain equal h rho g itself. since for a typical rock, the elastic limit is 30 into 10 to the power 7 Newton per meter square. The value of h rho g is equal to 30 into 10 to the power 7 Newton per meter square, or h is equal to 30 into 10 to the power 7 Newton per meter square, whole divided by 3 into 10 to the power 3 kilogram per meter cube into 10 meter per second square. This is equal to 10 kilometers. Therefore, the maximum possible height that a mountain can have is 10 kilometers, which is 1.2 kilometers greater than Mount Everest.